Recording, and I have audio. Excellent. Okay, so we are going to talk about the normal distribution. We started, I want to ease into this normal distribution. Not really ease into it. I want to put it in context. Okay, this is one of the things about this course. Why people, everything we cover builds on everything we have covered. So you need to understand, you need to know what we've already talked about in order to fully understand what we're about to talk about. This is a perfect example. We talked about, initially, about frequency distributions, where we talk about how do we analyze data. We've just got a big old pile of data, a population of 14 bajillion screws that were made in this plant. How are they distributed in terms of their tolerances? How far do they, how precise, how consistent are they manufactured to the same specs? Well, the first thing we have to do is be able to describe the entire population. And we can do that with numbers. Frequency distribution. How many of them fall within this much tolerance of their design? How many fall this far away from that? This far above the tolerance, this far below the tolerance, and they get binned, and they form a frequency distribution. And then that frequency distribution, eventually we can describe the population of all of those, the entire data set. And now we can talk about what we expect of it. How, we looked at certain measures of that description. We met that population. We talked about measures of central tendency, measures of variability, measures of position. We also snuck in this notion of normalcy and how that distribution could be shaped. And ideally, it would be a nice bell-shaped distribution. If you broke down the individual classes or bins into smaller and smaller sizes, it would become more, ideally, it would be symmetrically shaped around a central point, and it would be fairly narrow if you want it to, or it might be fat and spread out, but we could talk about the measures of central tendency as being mean, median, mode, range, or mid-range, not range, mid-range. And we noticed that if all of those values lined up and were the same value, that's when it was nice and bell-shaped and symmetrical. And if they got off from each other, then it was skewed one way or the other. But we could talk intelligently and quantitatively about how centrally symmetric this distribution was. We could talk about how fat it was, how much it spread out, or how close it stayed together in terms of measures of variation, which were variance and standard deviation. Range was a measure of variation. And then we start talking about position, measures of position. Where does a particular datum occur in that distribution? Where do we find it? Not just a datum, but that one in particular. And we found that, well, we could talk about a z-score, which is important. We're going to get back to that today, which was basically just how many standard deviations away from the mean is that particular datum. Or we could talk about, we could divide the whole population into 100 equal pieces and call it the range, divide the range into 100 equal pieces and call it the percentiles. Or 10 equal pieces and it would be deciles, or 4 it was quartiles. Then we got to talking about, once we realized we could talk about which percentile a particular datum was in the distribution, we realized, well, that's kind of like talking about if we chose a part at random what is the probability that our part would be in that, somewhere at that point in the distribution or less. And that brought us to the probability distributions, the discrete probability distributions that we talked about last week. Where instead of a population of data, we had a population of events that or outcomes of experimental trials. And though that became a distribution, not a frequency distribution, but a probability distribution. What are the probabilities that a given event or a given outcome would fall at any particular point in that distribution? Only we had developed equations for all of these measures of central tendency, of variability, of position, were based on the percentages of the entire population. Well, once we started talking about the distribution of probabilities, law of large numbers says that those values, those theoretical values, are going to be based on an infinite number of data, an infinite number of trials before, we would get the exact theoretical. Well, you can't divide anything by infinity or it goes to zero and it becomes meaningless. So we came up with these alternative equations for probability distributions. It didn't involve dividing by anything. Today, we're now going to go into that probability distribution we looked at first was based on discrete distribution, discrete probabilities. There were certain events, certain outcomes, because an event is actually a set of outcomes, a finite set of outcomes. Well, we then took that idea of, sorry, I got distracted by someone walking by in the hall. Should close that door. We turned this into a probability distribution. We came up with new equations, but these were discrete probabilities. There were finite sample spaces. Now, the infinity was the number of trials. But even though there was an infinite number of trials, there was still a finite sample space. There were only a certain number of outcomes that were possible. Now, we're going to extend that idea into a continuous distribution. So instead of saying, now we may still have a finite range, okay? For example, no, I don't want to get ahead. Let me not get ahead of myself. I need to take a breath because I got started behind the 8 ball coming in a minute late. I can't get that minute back. So stop, breathe, think about what you're saying. Now we're looking at continuous probability distributions. Now, the difference between a discrete variable and a continuous variable, you'll recall, is the discrete variable can only take on certain values. It cannot take on an infinite number of values. Continuous variables can take on an infinite number of possible values, even if it's limited to a finite range. Okay? For example, we talk about breaking up the measuring temperature. Well, the temperature, we can set the boundaries of each class, and we've talked about that. We can put a boundary between two classes so that in this class or in this grouping, they're only, everything is between 35 and 36 degrees Fahrenheit. But between 35 and 36 degrees, the temperature can be an infinite number of possible values. And in point of fact, the entire spectrum is still going to be a continuous distribution. on page 304, you'll see the four pictures at the top there. That shows what I'm talking about. You take that discrete distribution and you keep dividing each class into more and more classes. You divide the same range into more and more classes. So each class becomes smaller and smaller until you end up with a bunch of little bitty tiny rectangles that form a nice smooth bell curve. Well, when you take that final next step to the limit of those class widths becoming 0, you end up with a smooth, continuous, bell-shaped, symmetrical curve distribution. Now, in this case, it's bell-shaped and symmetrical. Okay, and it will be. Let's eliminate the vertical axis. Let's just look at the horizontal axis. There is your mean of the population. So your distribution and the limit that the class width approaches 0, the distribution becomes continuous. And even though I put a lot of wobble in my line, it shouldn't be there. It should be a nice smooth curve. Now, there's a couple of things about this you need to know. This curve extends all the way to minus infinity and plus infinity. And no matter how far out you go, it never, ever, ever makes it all the way to the horizontal axis until you get to infinity, which you can never get to infinity. So, yeah. All right. Well, pretty smart fella, named Gauss. I think they give you his whole name in the book here somewhere. Carl Friedrich Gauss. Yeah, Deutschland. Say again? Yeah. He came up with a mathematical expression that describes this nice smooth, this is called a normal distribution when it is bell-shaped and symmetrical about the mean. In fact, that's the definition right here on page 305. If a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, it is called a normal distribution. And this curve is called a normal distribution curve. Okay. Carl Friedrich Gauss came up with a really cool little expression. Nope, sorry, wrote that wrong. Okay. Y equals e to the negative x minus mu quantity squared divided by 2 times sigma squared, 2 times the variation, the variance. Okay? That equation describes this curve. Now let's look at this because this is important. I want to take y'all through this one step at a time so you see and understand how this equation describes that curve. So get out your calculators. Do you have an E button? E to the x? Okay. This is how you would actually calculate this curve. No, we're not, I'm sorry, don't, you can put your calculators down. We don't need to actually do the calculation. Do either of you understand what E is? No, E, the letter E, and mathematically. Okay, E is the base of the natural logarithm. Okay? I think that's a Y. Whatever. You've seen ln, the natural log function. Well, E is the base of the natural log function. If you asked for the base 10 log of 100, the answer would be 2. Why? Because 2 is the exponent that you would raise the base of 10 to the power of to get 100. Okay? Log base 10 of 10,000 is Jordan. You don't need the calculator, just count the zeros. 4. You raise 10 to the power of 4, you get 10,000. Therefore, the base 10 logarithm of 10,000 is 4. E has a numeric value. It's an irrational number. It has no finite number of decimal places, and there's no ratio of integers that will give you that exact value. But it is approximately 2.718 and some more. Okay? If you have an E button on your calculator, if you put in 1 and raise E to the power of 1, it'll give you the number E. Okay? It is an irrational number. It never terminates. There's no end to it. But it's about 2.718. So when you see the letter E, it's a number. That means this is actually written as 2.718 to the power of minus x minus mu, quantity squared, divided by 2 times sigma squared. Okay? That's literally what this means. Now, what is E? What happens when x is equal to the mean, when the variable x is equal to mu? This becomes 0. 0 squared is still 0. And 0 divided by anything is still 0. So when x equals mu, right here, this is 0, and y equals what? Anything to the power of 0 is always 1. Okay? So that means right here, this distribution curve has a value of 1. the distribution curve described by this equation. Now, once you go less than this, then the value of it falls off a bit. So if x is not quite equal to mu, then this is going to be, if x is a little bit less than mu, then it's going to be slightly negative number, but still very small. And therefore, the value of this will start to fall down. And the further out you go, the closer it will get to zero. Of course, it will never get all the way to zero. The same thing happens when you go, when x becomes greater than mu. This value starts to get smaller and smaller the further out you go. Of course, no matter how small this gets, it's still going to be slightly positive. It will never quite make it all the way to zero, but it will get closer and closer and closer. Now, if you were to do this integration, and we're not a calculus class, so we're not going to do this. That integral would equal sigma times the square root of 2 pi. Okay. That's the total. If you integrate this whole thing, what you're doing is you're calculating all of the area underneath that curve from minus infinity to plus infinity. All of the area under that curve comes out equal to that sigma times the square root of 2 pi. So, if we take Mr. Gauss's equation here, of y equals minus x, give me some more space over here. And we divide that by the total area under the curve, sigma times the square root of 2 pi. Remember what pi is. Pi is like e. It's an irrational number with no end to the decimal places. It's the number you get when you divide the circumference of any circle by its diameter. You always get that same ratio of pi, 3.14159, blah, 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 blah. Okay? Well, when you divide this equation by that value, now what happens when you integrate the whole thing to calculate the area under the entire curve? Let's go back over here. Now we're going to, instead of integrating just that, we're going to integrate well, you'll notice that this bottom is sigma and 2 pi. This is all constants. So they don't get integrated. You just pull those out. and you integrate just that. So that means that this total integral now, from minus infinity to plus infinity, is now equal to 1 over sigma times the square root of 2 pi times that integral, which equals sigma times the square root of 2 pi. So what do you get when you divide that by that? What does that now equal to? You divide any number by itself. Doesn't matter what the number is. It's always going to equal 1. Okay? Now this is important. Look at what just happened. We now have this continuous distribution. We now have this continuous distribution, from minus infinity to plus infinity, that has a total area under the curve of 1. If you add up all of the probabilities of all of the possible outcomes in a probability distribution, what must they all sum to? Always 1. This now sums to 1. Remember, anytime you're integrating, you're calculating the area under the curve, you're summing all of those little tiny rectangles. Under the whole thing, it sums to 1. This is now a continuous probability distribution. And we call this the normal probability distribution, or the normal curve. You'll also see it here referred to sometimes as a Gaussian distribution, because Gauss is the one who came up with this equation. Okay, and the statistics books don't really make this distinction, but I do. Come on, page, let go. I just want one of it. Thank you. And that's how pages get dog-eared. People think it's because people disrespect the books and fold down corners. No, they get dog-eared because they fight you won't turn the page. Statisticians do not generally make this distinction, but I do. Strictly speaking, this is not a Gaussian curve. This is a normalized Gaussian curve. When you erase that denominator that we divided by, just this top part is the Gaussian curve. But anytime you divide an equation by the sum of its integral, then you've normalized it so that the total area under the curve, whatever the curve shape happens to be, the total area under the curve of that normalized distribution will always equal 1. And that's where we get the word the normal distribution. Doesn't mean it's the least weird, the least strange. It means it's been normalized so that the area under it equals 1. Now, because it's, and I say that doesn't mean it's the least weird, but that's where the origins of the word. Now that you understand that's where the word normal comes from, Now I'm going to explain to you why actually it does still mean the least weird. So when someone says, well, oh, who are you to say what's normal? Like, well, normal is mathematically defined. It's plus or minus. It's the plus or minus 3 standard deviations of a Gaussian distribution under a plus or minus 3 standard deviations about the arithmetic mean of a Gaussian distribution. That's normal. Yeah. If you're further away from the mean than that, you're not normal anymore. No. Oh. We call this the normal distribution when it's nice, bell-shaped, and symmetrical. What is the mode of this? Just looking at it. What's the mode? Remember what the mode is? It's the class that occurs most often. The one that had the class or the group that has the most members that fall in that class and that within those boundaries. That's the mode. In this case, the mode is right there at the mean. What's the median? Okay, where would that be here? It's the median is the number that is the middle of the extents, right? Not necessarily the mean, not the average, but the middle between the highest and the lowest. Well, here you've got exactly the same number of data on this side as you do on this side. So we've got the mode and the median are also right there at the mean. If this data, if the distribution of the data in this continuous distribution were not nice and symmetrical about this, then this curve, depending on because remember, we're going to use this to describe empirical data, measured results. So if we measured the data and we found that it was actually something like this, now, here's your mode. Here's your median. And your mean is somewhere here. You notice they're no longer equal. They're quite different. This is, what would this be called? Left skewed. Okay? It could look like this. Mode, median, and mean. Now, the tail shoots off to the left because this one has been skewed to the right. But you'll notice that they're not. The mode, median, and mean start getting spread out. The further apart the mode, median, and mean get, the less normal this distribution is. The more weird it becomes. Okay, the more skewed it becomes. I give you a definition here on page 307 that says the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. Okay? All that. All this. What was this? Where we put mu? Okay. Remember, the horizontal axis here is not mu, it's x. Okay? This is the mean. When is the mean? When does the equation e to the minus x minus mu squared, when is it at maximum? When does it go to its peak value here? When x minus mu is 0. So, if x minus mu is 0, then what does that mean mu is right here? Okay, but what we're saying is x minus mu is 0. Well, if mu is the value of x, anyway, the point is when the mean is set to 0 and the standard deviation is 1, these would be minus and plus. Then you have that's what is defined as a normal standard deviation. And that means that in this area, you're going to have 34.13% of the total area under the curve. In other words, this area from here to here, the area would be 0.3413. The area here would be 0.1359. And did I get that right? Yes. This area would be 0.0215. And all the area here, from -3 on down to minus infinity, would be so if you took and integrated that equation from minus infinity up to -3, this would be the value of that integral. That's the total area under the curve from minus infinity to -3, 0.0013. If you integrated from -3 to -2, this is how much you would get. If you integrated from -2 to -1, this would be the value, the result. And if you integrated from -1 to 0, that's what you would get. Now, it's because this is symmetrical. You get the same values if you integrate those other sections. Now, here's how this helps. From here to here, this is 34.13%. So if you integrated from minus infinity all the way up to mu, you would get 34.13% plus 13.59% plus 2.15% plus 0.13%. What if you add those up? You get 50%, which is exactly what you would expect. Yeah. Right now I've done this based on x and mu. What if we converted what if our distribution doesn't give us a mu, a mean of 0? What if it has an average of 46? This is where that z-score we looked at comes in. What's the z-score? How do you calculate the z-score? There it is. Now, the z score for any given data, any datum, any value of x on any distribution, z is that right? X minus, yeah, that's right. The value of x minus the mean divided by sigma, by the standard deviation. And that gives you a number, which is the number of standard deviations that value is off away from the mean. Okay? So, if you're dealing with a distribution that does not have, that just didn't happen to have a mean of 0 and a standard deviation of 1, you don't know. You analyze the distribution and you find out that the mean is 46 and the standard deviation is 12. You can still calculate a z-score that will give you that datum's position relative to a normal distribution curve. I told him, I'm going to ask you, did you get this in your book? Handy dandy fold out? Got yours with you and everything. Yeah, it's going to be very handy when you're working on all these tables that are on here are included in your they're in the back of your book. But when you're working homework problems or doing the calculating, stuff, get this out, set it next to you so you can look at these values up on the table here without having to keep flipping back to the back of your book. This is how you will use this table once you've turned your value out of your distribution that you're looking for. You convert it to a z, then you can use this table to find out what percentage of the distribution is behind it, or what the percentage is above it. And we're going to go through how to do that next time. We're going to do that. We're going to cover that next time on Friday, how to do that. Although you will very likely be able to, you could start working the problems now, doing the homework. In fact, it'd be good if you did, because then you could have questions on Friday when we start. Yeah, we'll pick that up then, pick up there then, and get y'all ready to finish up the homework over the weekend.